This is John Whitaker for the graduate level probability class, and this is our 14th video lecture, and today we want to continue talking about moment generating functions and apply them to certain random variable types. So that's what we're going to get to. We're going to prove some facts that we just stated before, having to do with the addition of independent random variables that are either like normal. We had a statement about normally distributed random variables. If we add those two, then we get normally distributed random variables. And we're going to prove that fact using moment generating functions. We'll also look at some limit theorems. We'll start on that today as well. Okay, so first fact that we want to talk about has to do with the moment generating function for an exponential random variable. So it says if x is an exponential random variable with parameter lambda, of course lambda is greater than 0, then the moment generating function of x is phi sub x of t, which is equal to lambda over, I think it's lambda minus t, where t is less than lambda. So we want to prove this. And so in order to prove it, we're going to use the definition of the moment generating function. But let's start off with assuming the situation. So let's let x be an exponential random variable. With parameter lambda greater than 0. Okay, so an exponential random variable. Well, it was a continuous random variable. So let's recall the probability density function of x is, so it was f of x equaling, it was a piecewise defined function, I think it was lambda times e to the minus lambda x if x was greater than or equal to 0 and it was 0 otherwise. Okay, so we're trying to find the moment generating function, so it's phi sub x of t, and what that's equal to, by definition, is the expected value of e raised to the tx. Okay, that would be equal to the integral from minus infinity to infinity of e to the tx f of x dx. So that's equal to that's equal to the integral. Now, f of x a lot of times is 0. So the part, the x values for which f of x are 0, that part of the integrand, the integral, would be 0. So we only have to integrate from 0 to infinity. E to the tx, and then from 0 to infinity, f of x is lambda e to the minus lambda x dx. Okay, I can pull out the lambda. Integral from 0 to infinity, we can combine the e to the tx and the e to the minus lambda x. You get e to the, if you will, t minus lambda x times x dx. Now this is e to the something. The way that we integrate e to the something, remember we're integrating with respect to x, so the variable here is x. The way that we integrate e to the something is if we have e to the something derivative of something, we can do that through u substitution. The answer is just e to the something. So I have lambda there. I've almost got the derivative of the something sitting here. So e to the something, the derivative of something with respect to x is t minus lambda. Well, I don't have that. But I can put it there because it's a constant with respect to x, as long as I compensate by putting 1 over t minus lambda out front. And so I end up getting lambda over t minus lambda times, the answer to the antiderivative for this is e to the t minus lambda raised to x, and then I need to evaluate it as x goes from 0 to, forgive me, I know this is improper random, but I'm just going to say x equaling to infinity. Okay. Now, when we let, so here's what we have. I'm just going to rewrite it so I can see it. So it's equal to p sub x of t is equal to lambda times t minus lambda e to the t minus lambda raised to x, and here we're going to let x be 0 up to infinity. So we're supposed to stick in infinity first. Here's why we see that lambda has to be bigger than t. Okay, so if x is getting really, really huge, if t minus lambda is a positive number, then when I multiply it by something really, really huge, I get e to the really huge things, that goes to infinity. So we'll get that this doesn't exist. So what we need to make sure of is that the t minus lambda is a negative number, so that means lambda has to be bigger than t. So when lambda is bigger than t, this is exponent, this part of the exponent is negative. And as we multiply it by huge positive numbers, we get huge in magnitude negative numbers. And e to huge negative numbers goes to 0. So this is equal to 0 minus lambda t minus lambda. And here when I let x be, go to 0, or be 0, what we get out here is just e to the 0, which is just 1. Now, this minus out in front can be distributed to the bottom here, and so we get lambda over lambda minus t. And that's what we want to show, but I'll give a conclusionary statement. So, phi sub x of t for this exponential random variable is lambda over lambda minus t. Okay. Here's a fact, similar fact. If x is a normally distributed random variable, then with parameters mu and sigma squared, so we're going to talk about the moment generating function for a normally distributed random variable. Then the moment generating function of x is phi sub x of t. And what it's equal to is equal to e, I think it's e to the mu t is where I'll write it, plus sigma squared t squared over 2. We won't prove that, so that's the moment generating function. So here's the proof. we're going to let x be normally distributed. With parameters mu and lambda. Okay, so we're going to do this in mu and lambda. Mu is sigma squared. We're going to do this in cases. The first case is where we have a standard normal. So case 1 is where mu is equal to 0 and sigma squared is equal to 1. Then, so that's the standard normal. So the moment generating function p sub z of t, okay, is equal to the expected value of e raised to the tz, which is equal to, well, it'll be the integral from minus infinity to infinity of e to the tz times 1 over the square root of 2 pi e to the minus, it would be z squared over 2 dz. All right, so we need to figure out what that is. So that's equal to 1 over the square root of 2 pi minus infinity, integral from minus infinity to infinity. I'm going to combine the e's to the exponents, and I think what we're going to have is e to the, I'm going to write it this way, it's minus the quantity z squared over 2, and then we do plus t times mu, and then we have dz. Made mistakes, not t times mu, t times z. So I'm going to rewrite this as 1 over the square root of 2 pi, integral from minus infinity to infinity, getting the common denominator. This is e to the, I'm going to put out a minus. It would be z squared, and then this would be minus 2tz, all that over 2, dz. So that's what we have. So all I did was get a common denominator and factor out the minus outflow of the exponent. All right, now, by completing the square, on z squared minus 2tz, this will be equal to z squared minus 2tz. So we take half of this number, which just be t, and square it. So we have plus t squared, that's what we want, minus t squared, which is really equal to z, well, I'll stop right there. And I won't stop. Now, that's equal to, so here this will be z minus t to b squared minus t squared. So, our phi sub z of t, which is equal to 1 over the square root of 2 pi, integral from minus infinity to infinity, of e, so I'm looking over there, to the minus, and so I'm rewriting that z squared minus 2tz as this. So it's z squared, z minus t to b squared minus t squared, okay? And that's still all over 2 dz. And so I will rewrite that as 1 over the square root of 2 pi. Here, let us distribute that minus, so integral from minus infinity to infinity, e to the minus quantity z minus t to b squared over 2, and here this would be plus, it would be t squared over 2 dz. So the t squared plus 2 is part of the exponent. And now I can pull it, well, I can rewrite that as 1 over the square root of 2 pi. This will be the integral from minus infinity to infinity. And I'll rewrite this as e to the minus quantity z minus t to b squared over 2 times e to the t squared over 2 dz. And the e to the t squared over 2 that's sitting out here is a constant with respect to z, so I can pull it outside the integral. That's what I'm going to do next. So that's equal to, 1 over the square root of 2 pi e to the t squared over 2 and then we have the integral from minus infinity to infinity. I'm going to put this in parentheses. E to the minus quantity z minus t to b squared over 2 dz. And if you will, let me pull this inside this parenthesis. So 1 over the square root of 2 pi sitting right here. Now that parenthetical expression, especially if you pull in the 1 over the square root of 2 pi inside the integral, what you see is 1 over the square root of 2 pi that we're integrating. E to minus the variable that we're integrating with respect to, minus some number, to b squared over 2 times, and I'll say 1. And what that looks like then, when we pull 1 over the square root of 2 pi involved, it looks like you're integrating the PDF of a normally distributed random variable with parameters t and 1, sigma equal to 1. Sigma squared equal to 1. And so we know that that integral is just equal to 1. So this ends up getting e to the t squared over 2. That's what we get. So in this case, of z being the standard normal, p sub z of t is equal to e to the t squared over 2. And remember what we're trying to show is we're trying to get e, so for any normally distributed random variable, we're trying to show that its moment generating function is e to the mu t plus, it was a sigma squared times t squared over 2. But with the standard normal, mu t, the mu is 0, so 0 times t is 0, plus sigma squared is 1, so 1 times t squared all over 2. So it does hold true, the statement, when z is standard normal. Okay. We got it in this case. For case 2, okay, and so we're going to really use case 1 to get case 2. We're going to say, suppose mu is different from 0 or sigma squared is different from 1. Note, x is equal to sigma z, that's something we proved before, plus mu. So that's the way that you can generate the normally distributed random variable through an algebraic combination of the standard normal, which is equal to, so the moment generating function for phi, the moment generating function for x, I should say, is equal to the expected value of e raised to the tx. But now I'm going to substitute what x is equal to. And so when I do that, I get, so phi sub x of t is equal to, okay, so here it's the expected value of e raised to the t times, now x is sigma z plus mu, which equals to the expected value of e to the sigma tz plus t mu, which is equal to the expected value of the function e to the sigma tz times e to the t mu. Now, this expected value is with the random variable x or z, okay, with z. And here, this is equal to, so the expected value of t times mu, what t is for a particular t value is fixed, is definitely constant with respect to z. So it can be pulled out of the expectation, so t mu times the expected value of e to the sigma tz, and that's equal to e to the t mu. And what this is the moment generating function for the standard normal. So phi sub z evaluated not at t, but at sigma t. So that's equal to e raised to the t mu. And what this will be, remember, phi sub z is nothing more than whatever's here squared all over 2. So it's e to that. So it'd be e to the t squared over, sigma squared. Yeah, sigma squared t squared all over 2. And then when we rewrite this with only one exponential by adding, we have t mu plus sigma squared t squared over 2. And that's what we wanted to show. So that proves this fact. Now, one of the things I forgot to do, and I'm sorry, for the exponential. So let's go ahead and do that now. So recall for the exponential random variable, with parameter lambda phi sub x, so I'm going to call the exponential random variable x. What was it? I think it was of t. I think it was lambda over lambda minus t. So what I forgot to do was to verify that, we could use the moment generating function to come up with the expected value for this random variable as well as its variance. And so I would like to do that. I meant to do it earlier. Okay, well, what was the expected value for an exponential? It was 1 over lambda. What was the variance? It was 1 over lambda squared. That's what I want to show you using the moment generating function. So phi sub x prime of t. Well, I'm going to rewrite phi sub x in a more classical way, a more convenient way, in order to take its derivative. So I'm going to rewrite it as lambda times lambda minus t raised to the minus 1. So the moment generating function is equal to lambda. So I'm taking the derivative, I should say. So what do I see here? I see a constant times something raised to a power. How do you take the derivative of a constant times something raised to a power? You write down the constant, you bring down the power, you write down the something to one less power, and then you have to, by the chain rule, take the derivative of what was being raised to the power. Now, I'm differentiating with respect to t. So this would be the derivative of lambda minus t with respect to t is minus 1. So that's equal to, well, it will be lambda over, I'll just leave it this way, lambda times, so the minus 1 and minus 1 makes it positive, lambda minus t to the minus 2. So the first derivative of the moment generating function evaluating at 0, let me write down, what is it that I find when I evaluate that at 0? It's the expected value of x. equals, so here that would be lambda minus 0 to the minus 2, which is lambda over lambda squared, because lambda minus 0 is lambda, lambda minus 2 is just lambda squared, and that's 1 over lambda. And that's what we were expecting. Okay. Note, the expected value of, well, let me just start off by saying phi sub x double prime of t. So if I take the derivative of this guy here, it would be lambda, so I say something raised to, I say constant times something raised to a power. So I write down the constant when I'm trying to take its derivative. I write down the something to 1 less power. I take the derivative of the inside. Oh, I forgot to bring down the power, so minus 2. Okay, so you write down the constant. Then you bring down the power. You write down the something to 1 less power. Then you have to take the derivative of the inside, which is minus 1. This ends up being 2 lambda, I'll say, over lambda minus t to the 3rd power. So the expected value of x squared for this exponentially distributed random variable would be equal to the moment generating function second derivative evaluated at 0, which will be 2 lambda over lambda minus 0, that's just lambda, to the 3rd. So it's 2 over lambda squared. So from that we can calculate the variance. So the variance of x, which you'll remember by formula, is the expected value of x squared minus the expected value of x 2b squared. I just calculated that for the exponential. It was 2 over lambda squared minus, this was 1 over lambda, b squared, which would make it 1 over lambda squared. And that's just equal to 1 over lambda squared. And that's what we were hopeful to get. Let us recall, if x is normally distributed, with parameters mu and sigma squared, then the moment generating function of x, t, that's equal to, so it was e to the t mu plus sigma squared t squared all over 2, that part over 2. Okay, so let us find the expected value using the moment generating function for a normally distributed random variable. Remember, our answer is supposed to be mu, and the variance is supposed to be sigma squared. We'll find both. Okay. So, again, phi sub x of t, let me write it right here, is e to the t mu plus sigma squared t squared over 2. So its derivative. Okay, so we're taking the derivative of e to something. So I'll write down e to the something. And now I have to multiply that by the derivative of the something. Remember, I'm differentiating with respect to t. So here's an addition within the exponent. So how do I take the derivative of an addition? Well, you take the derivative of each part. So the derivative of t times mu is just mu, plus the derivative of sigma squared over 2 times t squared. Well, sigma squared over 2 times the derivative of t squared, which is 2t. So the 2 that I would bring down and this 2 would cancel. So I'm left with sigma squared t. So the expected value of x would be equal to the moment generating function's derivative evaluated at 0, which would be e to the 0 mu plus sigma squared 0 squared over 2 times mu plus sigma squared times 0.
this is exponent-wise is 0, e to the 0 is 1, this part is 0, so mu plus 0 is mu, 1 times mu is mu. And that's what we were hopeful to get. Also, the second derivative of the moment generating function, so I take the derivative of the first derivative, and that's going to involve the product rule. So I write down the first, times the derivative of the second. The derivative of this function with respect to t is just sigma squared, plus, now I write down the second, times the derivative of the first. This is e to the something, but that's what I just had here. And so really, this is its derivative. So I've written down this, I'm going to multiply by that again, so squared times e to the t mu plus sigma squared t squared all over 2. So the expected value of x squared is equal to the second derivative evaluated at 0. Okay, so when t is 0, this part becomes e to the 0 sigma squared plus, this is going to be mu only from this parenthetical expression, to be squared, so it's mu squared. And this is e to the 0, which is just 1. So we get sigma squared plus mu squared. So the variance of x is going to be equal to the expected value of x squared minus the expected value of x to b squared, which is equal to sigma squared plus mu squared minus the expected value of x was mu, and we're squaring it, and so we'll just get sigma squared, which is what we should get. Okay. Next, I want to re-examine the fact. Well, no, sorry. Next, I want to present a new fact. Here's what it says. It says, really easy. If x and y are independent random variables, then the moment generating function for x plus y is the same thing as the moment generating function for x times the moment generating function for y. Real easy to see. Here's the proof. So let x and y be two independent random variables. Then these of x plus y of t, by definition, is the expected value of e raised to the t times x plus y, which is the same thing as the expected value of e to the tx times e to the ty. Now, we had a fact about if we had two independent random variables, x and y, and we were looking at the expected value of h of x times g of y, then that's the same thing as the expected value, our previous fact, of e to the tx. It's the expected value of, so h of x times the expected value of g of x. So here the g of x is e to the ty. But that's just equal to, this is the moment generating function of x times the moment generating function of y. And that was what we were trying to prove. So that was easy. Okay. Next, we want to relook at, there's a fact here we want to do. It says the following. It says, we're not going to prove this, but there exists a one-to-one correspondence between the moment generating functions of random variables and the distribution of random variables. Okay. What this fact means is the following. That each random variable can be classified, characterized by its moment generating function. So what I mean is that when you see the moment generating function for a random variable, if it fits a certain type, then you could say, hey, based on the moment generating function, we know the random variable was this type of random variable. Could be a normally distributed random variable if its moment generating function has the appropriate form. Okay, so let's look at some examples. And these examples are really facts that we stated before we didn't prove. So let X and Y be binomial random variables with parameters. So M and P, that's for X, and N and P for Y. Then X plus Y, well, I messed up. Don't forget, what I mean to say is that we let X and Y be independent random variables. Be independent. Then, phi sub X plus Y of T, okay, that's equal to phi sub X of T by previous fact we just proved, times phi sub Y of T, where the phis are the moment generating function of their respective random variables involved. X plus Y, X or Y. Which equals to, now phi sub X of T, I know what the moment generating function for a binomial random variable with parameters M and P are. it's p times e raised to the t plus 1 minus p raised to the n. And then this guy, moment generating function, will p times e to the t plus 1 minus p raised to the n. And so we can rewrite that using rules of exponents as p times e to the t plus 1 minus p all raised to the n plus m, or m plus n. Now, that is the moment generating function of x plus y, where they're binomial and independent. And it fits the right form, it fits the form of a moment generating function for a binomial random variable. And so what we'll say is, so x plus y is a binomial random variable with, I'll write right here, parameters. Well, the parameters are, the first one is the exponent. So here it's m plus n. That's what we said before in our fact. Several lectures ago. And p, the probability of success. So that's the way we can prove the fact that we stated. We also had a similar fact when we were dealing with normally distributed random variables, and I want to look at that next. Okay, so I'll say that as an example, what we'll do is we'll let x and y be two independent, normally distributed random variables with parameters mu sub 1 and sigma sub 1 squared, and so that's the parameters for x. And for y, they're mu sub 2 and sigma sub 2 squared. Okay. Then, if we look at the moment generating function of p of x plus y acting on t, because of independence, this is the moment generating function of x times the moment generating function of y. Now, they're both normally distributed, and I just learned what the moment generating function forms for those are. So here it is e to the mu 1 t plus sigma sub 1 squared t squared over 2 times e, let me make this e a little bigger. E, similarly, this is going to be mu sub 2 times t plus sigma sub 2 squared times t squared all over 2. Okay, so I can add those together, add the exponents together. So what I get is e to the, well, it would be mu 1 t plus mu 2 t, those are like terms, plus sigma 1 squared t squared over 2 plus sigma 2 squared t squared over 2. So that's the power. That's equal to e, and then I can factor out t, so I get mu 1 plus mu 2 times t. Then this would be plus, I can factor out a t squared, I'll put it here at the back, and it's over 2. And what I have is sigma 1 squared plus sigma 2 squared. And that fits the form for a moment generating function. We got what? Moment generating function of a normally distributed random variable, where their parameters will be mu sub 1 plus, mu sub 2, and sigma sub 1 squared and sigma sub 2 squared. So that's what I'm going to write. And that's what the fact was that we had stated earlier a few lectures ago. Let me write that down. So x plus y is normally distributed. With parameters. mu1 plus mu2 and sigma 1 squared plus sigma 2 squared. Okay. All right, so the next thing we want to do is these, we're going to conclude with something called limit theorems. So there are some really important facts in probability, and we're going to start looking at some of those. So that's our next topic, limit theorems. And we're first going to do some preliminary theorem. One is called a theorem, it's called Markov's inequality. So what does Markov's inequality say? It says the following. It says, if x is a non-negative random variable and a is greater than 0, then the probability that x is greater than or equal to a is less than or equal to the expected value of x over a. So that's Markov's inequality. We're going to prove it. And we're going to prove one more statement called Chebyshev's inequality, and that's all we're going to do for this lecture. So here's the proof. We're going to let x be a non-negative random variable and a be greater than 0. Now this proof is a type of proof that I call construction type proof. So they kind of say, well, look at this. Why you would look at this? Because it works. But how to come up with looking at this, that takes some innovation. So for me, I just remember we have to look at this. So note, if you define this random variable I to be equal to 1, if x over x is greater than or equal to a, and it's 0 otherwise. Okay, so that's what we're defining is this random variable I. It depends on what x's relationship to a is. Of course, that's what our statement has to do with, x relationship to a. So here's the claim. The claim is that I is less than or equal to x over a. So whatever numerical value x over a is, I is going to be less than or equal to. So let's work on the proof of that claim. And we'll break it into two cases. So case 1 is that x is greater than or equal to a. Then, when x is greater than or equal to a, let's talk about I. So I is going to be equal to 1. Also, since x is greater than or equal to a, which is greater than 0, x over a is going to be greater than, so if I divide everything by a, it's going to be greater than or equal to 1. So I'm just looking at this part of the inequality, I'm dividing everything by a. It's a positive number, so I don't have to switch the sign of this inequality. I get x over a over here, and over here I just get 1. And, well, in this case, 1 is the same thing as I. So I is less than or equal to x over a in this case. So for case 2, we'll say that x is less than a. Then what's I? I is equal to 0. And because x is non-negative, what we have is, so this is 0 less than or equal to that. So we have 0 is less than or equal to x over a. So I'm just dividing both of these guys by a is positive. So that says that I, which is 0, is less than or equal to x over a. So that ends the proof of claim. All right, so since I is less than or equal to x over a, then, and I'm not going to go through the details, the expected value of I is less than or equal to the expected value of x over a. So look, if this random variable's outputs, I'm going to argue it, but I'm not going to write any words. If this random variable's output values are always less than or equal to this random variable's output values, you say, what's the expected value of this one in comparison to this one? Well, the one with the smaller output values, its expected value is going to be, its average, is going to be less than the average of the bigger random variable. That's what we have. But this is equal to the expected value of x over a. Aha. Now note, the expected value of I, well wait a minute, what was I? I was either 1 or 0. That means it's a discrete random variable. I only got 2 output values, so its expected value is the sum over its output values, which are 0 and 1, of I times f of I. Well, when you have 0, 0 times f of 0, that's nothing. So really it's just 1 times f of 1. It's just f of 1. What's f of 1? That's the probability that I is equal to 1 for the PMF. So what is the probability that I is equal to 1? Well, that's the same thing. When was I equal to 1? When x was greater than or equal to a. So that's the probability that x is greater than or equal to a. So here, the expected value of I is the probability that x is greater than or equal to a. That's this part. So that's going to be less than or equal to the expected value of x over a. And that's what we were trying to prove. That proves Markov's inequality. Well, from Markov's inequality, we get an inequality called Chebyshev's inequality. That's what we're looking at right now. So Chebyshev's inequality says the following. So it's a theorem. What it says let x be a random variable with finite mean mu and finite variance sigma squared we're going to let k be a number that's greater than 0. Then the probability that x minus mu, so that's what that is greater than or equal to k, is going to be less than or equal to sigma squared, that's the variance, over k squared. We'll prove that. So we're going to let x be a random variable with finite mean mu and finite variance sigma squared. Okay. Look, we won't be talking about the probability of x minus mu inside absolute values. So what I'm going to do is I'm going to concentrate on that x minus mu inside absolute values for a short time. I'm going to prove a fact about it. So here's a claim. Okay, so my claim is x minus mu inside absolute value to be greater than or equal to k if and only if x minus mu squared is greater than or equal to k squared. Let's prove this claim. Prove this claim. So proof of claim. So here, it's an if and only if, so we'll start in this direction. We'll let absolute value x minus mu be greater than or equal to k. So what does that say? It's very easy to see. Well, the absolute value is nothing more than the square root of x minus mu to b squared. And so that's greater than or equal to k. So the absolute value of x minus mu is the square root of x minus mu squared. Since f of x equaling to x squared is an increasing function, and we got k is bigger than 0, so we can apply x squared to both parts. So it's on 0 to infinity. That's where it's an increasing function. Then when I square both sides, I maintain that inequality. So what we have is x minus mu squared is greater than or equal to k squared. So that proves one direction of the claim. Now, suppose x minus mu squared is greater than or equal to k squared. And what we're trying to show is the absolute value of x minus mu is going to be greater than k. Well, since let's call it g of x, equal to the square root of x is an increasing function. Then, when I take the square root of both those parts, we get the square root of x minus mu squared has to be greater than or equal to the square root of k squared. Now, since k is greater than 0, what we have is, well, the square root of x minus mu squared is defined to be the absolute value of x minus mu, and that's got to be greater than or equal to k. So that's what we have. So that ends the proof of claim. Okay, so what are we interested in Chebyshev's inequality? Well, we're interested in the probability that the absolute value of x minus mu is greater than or equal to k. Well, that's the same thing. It's probability of this, the same set, of x minus mu squared being greater than or equal to k squared. Now, here's the thing I want you to know. Is that x minus mu squared is a non-negative random variable. So applying Markov's inequality here's what we have. what will we have? We have the probability of absolute value of x minus mu, whoops, being greater than or equal to k, is equal to the probability that x minus mu squared is greater than or equal to k squared. Now, Markov's inequality is less than or equal to, it was the expected value of this random variable, so x minus mu to b squared, over k squared, but the expected value of x minus mu b squared is nothing more than the variance of x, which is sigma squared over k. And so that proves the Chebyshev's inequality. That's enough for today. Thank you very much for your time and patience.